Record on this computer. Okay, I wanted to spend a little bit of time talking about the solutions to homework set 3. In particular, how do you know when there's an infinite number of solutions to a system of equations? So here's the system of equations. Maybe I can zoom in or something here. Nope, it won't let me. Yeah, yes, it will, right here. Okay, so here's the system of equations. It's parameterized by alpha, beta, and delta. And I said, if alpha equals 1, what must beta and delta be in order for there to be an infinite number of solutions to the system of equations? Well, it has a unique solution if the determinant of this matrix is equal to 0. But if it's not equal to 0, it'll have a unique solution. So it may have multiple solutions, infinite solutions, if it is equal to 0. So that's the first thing you would do. I said that here. If there are infinite solutions, the determinant must equal 0. And since alpha equals 1, here is the determinant. If you set alpha equal to 1, you get this -5 minus 9 beta plus 1 equals 0, which is written, where is it? Written here. You can actually just solve for beta. Beta equals -4/9. However, to find delta, some people looked at these solutions that you get from Cramer's rule and said, well, let's just see when the numerator here equals 0. And that happens to work, but I don't think that will always work. I don't think that's always a, just to say, well, 0 over 0 is an indeterminate form, and therefore that's got to be what the solution is. Let's look when the numerator is 0. I don't think that quite always works. So here's a way that's a little bit better. To find delta, just solve the system of equations using substitution. Here's 3 equations. You can solve them for x, y, and z as best as you can in order to simplify the equations by using substitution and eliminating variables until you get to a point where it's only consistent if delta equals some value, and that must be the value of delta. The alternative case would be, well, if you choose any other delta, you get no solution. But if you choose this particular delta, you'll get infinite solutions. It's kind of like saying x equals x. Well, x equals x is always true. If I said x plus 1 equals x plus delta, this is always true if delta equals 1. And it's never true if delta is not equal to 1. So that's how we should be thinking about this value of delta. It's something where, it'll make everything consistent or it'll blow everything apart. So what I did was just use substitution here from the very last equation. The last equation was, I can solve for x equals 2 minus 5z, and plug that in. Then solve for y. In this equation here, you get y equals 4 minus 9z. So I've solved for x, I've solved for y. Plug both of those into this first equation, alpha times x, use what you have in terms of z there, beta times y, use what you have in terms of z there. You'll have nothing but z's and deltas on the top. And it will turn out that the z's disappear. You get this equation here, it simplifies to this equation. The z's, minus 5z, here's a plus 4z, here's a plus z. The z's just disappear. And all you're left with is this equation with delta that has to be true. And in other words, you can solve for delta this way. It happens to be 2/9. So that was this method, which, I hadn't taught you how to do this before, which made it a tough question to answer. And I don't think anybody got it the way I would have. I would think of as a legitimate solution. But actually, some people did get 2/9, and congratulations to those people. But reading your homework, as far as I could tell, you just somehow got this. You took the numerators here of these fractions and set them equal to 0, and didn't really explain why you were doing that. You just did it. But anyways, I'm still happy that you got the right answer, and I gave you a small amount of extra credit for having done that, or bonus points for having done that. Okay, but that's all I have to say about these solutions. You guys can see them yourself. Today we were going to finish up talking about partial differentiation and the Hessian matrix. which is good because you'll have a quiz on that at the end of class. Let's have quiz 3 at the end of class today. That way you can just leave after the quiz. You don't have to stick around for more lecture after the quiz. And I would like to talk about total derivatives as well. So we'll, I said that Tuesday would be a review. I think it'll be a review in as much as we get finished talking about total derivatives. After we're done talking about total derivatives, and the rest of next Tuesday's class will be a review for the final, which will be given out on Thursday. No, sorry, I said final, I meant midterm. Midterm on Thursday. Next Thursday is the midterm exam. Okay. Do you guys have any questions? I'm gonna pull up this slide about partial derivatives again and the Hessians. We had it last class. Let's continue where we left off, which is right here. I wish I could see slideshow from current slide. Sit from current slide. There you go. Remember, these were what I would call the higher order partial derivatives, the second order partial derivatives. And when you have a function of more than one variable, you get this complicated mixture of partial derivatives. Some of them are be like fxx, the same variable twice. Some of them could be like this, fxy, where you first take the partial derivative with respect to one variable and then the other. You could imagine a function of 3 variables too, fxyz. Then you'd have a bunch of these, you'd have fxz, fxy, fyz, fxx, fyy, fzz. You could imagine there's a more complicated structure of partial derivatives that exist when you have functions of higher variables. So we talked about that. We talked about what the Hessian matrix is. It's just a way to organize all of these second order partial derivatives into a matrix. So you have one function, f, and you have this giant matrix of its partial derivatives, where the dimensions of the matrix are n by n, where n is the number of variables of the function, input variables in the function. Okay, remember that? I gave you this example last class, and I think we got this far. Here's a function 2x squared y plus 3y squared. What's its Hessian matrix? Remember, for a 2 by 2, it's just this matrix of partial derivatives written here. You should be able to read this as you take the function f with partial derivative with respect to this first subscript x, and then again with the second subscript x. That's how you should read that. And you get 4y for x. You get 4x for these cross partials, and you get 6 for fyy. We did that last lecture. So ask me if you have a question about that, how you get here. Does anybody have a question over how we get to this matrix right here? Nobody said anything. Let the record show there was no question asked. Okay. Here's a question I don't think I got to last class. What's the value of the Hessian matrix at the point f, at the point 1, 2, or f of 1, 2? What do you think the answer to that is? How do we calculate a Hessian matrix at a point? Is it possible to do that? Sure it is. I think you guys know what to do here. You just plug in x equals 1 and you plug in y equals 2 and you get another matrix. You get a matrix of numbers, right? Could you answer this question? What is the value of the Hessian matrix at f1, 2?
Do you plug the x and y, the 1 and 2, into the x and y in the matrix or in the original formula?
In the matrix. So if you let's take Jordan's, he had this idea that, okay, you could plug x, y in 2 different places. You could plug it in here, or you could plug it in here. Just as a warning, if you had plugged it in the original function, you would essentially be saying f is a constant, and therefore it doesn't really have derivatives anymore. And you don't want that. What you do want is to say, no, f is this function which varies with respect to x and y in this particular way. Now we want to see, how does the function vary when x equals 1, x equals 2. You need to plug those into there. Maybe I should do my annotation again just to get this point home. You plug this 1 into there and also there. You plug this 2 into there, right? Because that's what I'm asking. What is the value of this Hessian matrix at this particular point? And the answer should be on my next animation is right there. 8, 4, 4, 6. Okay. We're gonna take a closer look at what this means, this 8, 4, 4, 6 in the next slide. I think. I want to clear my drawings. Okay. Next slide. This slide is about concavity and convexity of a function. And remember, there's this notion that we have that you probably, let me go to the, how about the whiteboard in this case? There's this notion that you probably have from talking about functions of one variable that, here's a function in green. Here's, f of x here. And is it concave or convex? I would call this concave. It's concave. Why it's concave? Because it looks like a hill. Use this point here at the top of the hill, but also because f double prime, not f prime, but f double prime is negative. That means the slope is always decreasing. You think about the slope at any time. Here I'll draw some slopes in red. Here's a slope, red. Here's another slope in red. Here's another slope in red. Here's another slope in red. You can see how the slope is positive here, 0, negative, negative. It's always decreasing. And you have this notion, f of x is a concave function because f double prime is less than 0, right? You would also have the same notion for convexity, the reverse. The function is convex if f double prime is positive. Okay, what I'm saying now is that this same concept applies to functions of more than one variable, except there is no f double prime when you're talking about, oops, I don't want that, but functions of more than one variable. What instead you need to do is talk about the Hessian matrix. Let me clear all of this, clear all these drawings. I can't draw for you. For me to draw a function of more than one variable, it has to be at least 3 dimensions, at least. And I'm just not good enough to draw that. But you still have this concept that, what if, would you be okay if I drew, I just feel like I'm going to do more harm than good if I try to draw it because it's hard. I'll just draw the axes. I'm not going to draw a function. Maybe how about just some axes? Like here's a z-axis. Here's a, what is this? X, and then here's a y-axis. It's coming in and out of the plane of the. And so, really, what you want to say for some function is it concave? Is it, what's going on? I said I wasn't going to even attempt to draw it, but here's this sort of green functional thing where I don't know what's happening here. Right here is this point, and you can go either direction, and it looks kind of like a bowl that you could store water in, right? I don't know how you can even draw this 3-dimensional thing, but if you're really good with your imagination, you might see that it's like there's this point here that's maybe at the bottom of this bowl, and then this is a convex function, convex. Here's, what did I say? This was the x-axis, this was the y-axis, and this is the z-axis. What do you guys think? Am I doing more harm than good by trying to draw a 3-dimensional thing? I want to convey this idea that here's a function f of x and y, x comma y, So it doesn't really make sense to say f double prime anymore, but it does make sense to talk about the Hessian function. If the Hessian has this property, well, it's positive definiteness, but I think for this class, I don't really teach you much about being positive definite. I just give you something that's equivalent to being positive definite, and to say, well, the function is convex if, I'll say this, if H is positive definite, which it's like, it takes me more time to even explain what it means to be positive definite. The actual faster way to do this is to say fxx is positive, right? You can kind of see that. Fxx is positive. Well, that's kind of like the bowl shape just in the x dimension. But also, there's this other thing. The determinant of the Hessian matrix should be positive as well. That's the key. I've been teaching you what determinants are and what Hessian matrices are, and they're coming together here to say that if the determinant of the Hessian is positive, then we can say that f is convex, because what do you get? Fxx times fyy. What is the determinant of the Hessian matrix? Let me go back to my slides now. Let me stop sharing this and share something else, which is this. From current slide, please. Okay. So what I've written here is what I was trying to say. If I take any function f, which is, for simplicity, let's say it only has two variables, x and y, and has an Hessian matrix H, we can say that f is concave in some region, R is the region, if fxx is less than 0. That means the partial derivative of f with respect to x twice is less than 0. That's, remember here I'm talking about concavity first. And the determinant of h is greater than 0 in R. We actually need both of those to be true. That is equivalent to saying f is concave. What about convexity? Well, it's the reverse, kind of. Just like before when we were talking about one variable, you had this idea, well, f double prime positive is convex, f double prime negative is concave. You still have that here where it's fxx, negative is concave, positive is convex. But look at the determinant of the, look at this thing here. This does not flip. So be careful here. Don't just think that concavity is, convexity is positive fxx and positive determinant, and concavity is negative fxx and negative determinant. That would be wrong. Actually, you need this determinant to be positive in both cases. This may seem...
What would it look like if the determinant was negative?
If the determinant of the Hessian matrix is negative, then you can say it's neither concave nor convex.
So that would be more of like a linear situation?
So there's this weird thing that actually, so yeah, linear would be a case. I wouldn't say it's strictly concave or strictly convex, which I'm fine. Let's not make that distinction in this class. Let's just say the linear functions are not concave and they're not convex. But there's a whole richer set of possibilities. I'm glad you asked this, Jordan, because when you have these multiple dimensions, you could think of a saddle point. Do you know what a saddle point is? A saddle, can I draw it? I'm sorry, I'm gonna be awful drawing it, but I still want to try. Here's what I'm going to say. Oh, I got to clear this. Here's what I think a saddle point looks like. In this axis, it looks like this. And in this axis, it looks like this. And so, it's 3 dimensions. These are all going like this. And in the other directions, it's going like Oh gosh, that's horrible. But you know, there's this point here where it kind of looks like it's convex in this dimension, but if you checked and looked the other way, it would look like it were concave. That's called a saddle point. You know what, like a horse, a saddle that you put on a horse, it's sort of front back. If you look from the horse's head to the horse's behind, it has this. Can you see while I'm doing this? It has this convex shape. But if you go from the horse's side to the horse's other side, it has this concave shape. Thus the name saddle point. A saddle point is one where maybe everything is flat. It's like a perfectly flat point, but it's not concave or convex. In fact, it's kind of both, depending. The truth is it's neither, but if you just looked at one dimension, it would look concave. And if you looked at the other dimension, it would look convex. You know, just like if you put a drop of water in the middle of a saddle, a horse's saddle, it would go to either the left or the right side, right? It wouldn't go forward because the saddle kind of slopes up forward, and it wouldn't go backwards because the saddle slopes up backwards. But on the left, where your legs go, because humans are riding this horse and they want their legs to fit on either side, so you know the water would drop down the left or the right where the person's legs are. Okay, so long way of saying, if the determinant H is negative, you should kind of think of that as this case here where it's like a saddle point. Of course, it might not be. It might be even stranger than this. There could be multiple ways in which it's you know, locally convex or locally concave, depending on which direction you're thinking of. And so it's my real answer is it's too complicated to say anything about what's going on when determinant H is negative. And in general, we just say it's not convex and it's not concave. Good question. Stop share. Okay. Let's go. I do want to share the slides again. Let's go back to the slides. And where were we? Current slide. Okay. Oh, by the way, the test becomes more complicated for larger, more than 2 dimensions here. There's n dimensions. I sort of think, you know, look, you can look that up in your book, in your textbook, or some other thing. I don't really feel like testing you about that in the class because you need to learn more about what matrices, like matrix theory, like what makes a matrix positive definite or negative definite, and it's not that hard. But let's just say it's more complicated for more than 2 dimensions. Here's an example. Use the Hessian to test whether the function fxy, blah, 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 is concave or convex at the point 1, 2. This is, by the way, the exact same function we just did. We just did this one for the Hessian. So here's a function. The question is it concave? Is it convex at the point 1, 2? You have to check. As a reminder, this is what we got for the Hessian matrix at the point 1, 2. Remember, Jordan asked, should we plug in the yx there or there? The answer was plug it in here after you've determined the Hessian, then plug in the points x equals 1, y equals 2. You got this, 8, 4, 4, 6. Now the question of whether it's concave or convex is, first to just look at what's in the top left. And is it positive or negative? And you see it's positive. That actually means it could be convex. Could be convex. It can't be concave because this would have to be negative for it to be concave. But because it's positive, it could be convex. But we're not done. We also need to check that the determinant is positive. You can probably look at this and see, yes, the determinant is positive. Whatever 48 minus 16 is, that's the determinant. So yes, f is indeed convex at the point 1, 2. Does that mean this function's always concave? Did I say concave? I meant convex. F is convex at the point 1, 2. Here's my next question. Over what range is this function convex? What am I asking here? I'm asking, what are all the possible values of x and y that would make this function be convex? You guys want to try this? I would love it if you give it a try. Try to answer this question and don't just look at my PowerPoint slides and see what the answer is and then give that answer back to me. Try to figure out how to solve this. Maybe you think it's always convex. Maybe you think no matter what x and y are, this will be a convex function. I can tell you right now that's not true. There's going to be some values of x and y where this function will not be convex. Anybody have an answer, by the way? If you're paying attention? Only one person with their videos on. The rest of you may not even be there. You could be getting a snack, going to the restroom, who knows? Watching Bridgerton on Netflix. Anybody? Oh, sorry. Somebody said something. Kai, you have an answer?
Yeah, so since like f of x is 8.
I'm sorry.
Is that I'm just like thinking about it, but
okay. But what did you say? F of x equals 8?
Which is above 0, which it has to be like convex for it to be like above 0. So
so I still didn't get with the first thing you said. What, like, how should we start this problem?
I don't know.
Okay, that's all right. I can help you. That's what I'm here for.
I mean, for any range like of f of x, that's above 0.
Good. You're saying use this condition here?
Yeah.
You want to see when is f(x) above 0? Great. What's the answer?
Well, the answer is 8 for.
No. So you don't know that that's going to be 8. It's only 8 at this point 1, 2. So right now forget about the point 1, 2. I'm asking a new question. This is a new question. Over what range is this function convex? So forget this point 1, 2.
Okay, so
look right here. See what I circled?
Yeah.
That's f(x). I want to know when is that positive? When is 4y positive? Give it me in terms of y. When is 4y positive? It's kind of just divide both sides by 4. You get y has to be positive, right?
Yeah.
Okay, so that's part of the answer. Part of the answer is that y has to be positive. You know that because if y is not positive, then this first condition won't be true. Do you agree?
Yeah.
Okay. Is anybody else? We're not done though. Anybody else want to help me with the rest?
Yeah, so doesn't the determinant also have to be greater than 0?
Perfect. Give me a number. Give me an equation for that. When does that happen?
This would be 4y times 6, so that's 24y.
Perfect.
minus is that 16x squared?
Perfect.
And then I guess you set that greater than 0.
Perfect. You guys see what he did? He said, well, we need the determinant to be positive. When does that happen? It's when 24y minus 16x squared is positive. Now we have to think about when does that happen? I mean, all you can do is, so this is essentially the right answer. I would like for it to be simplified a little bit, just for my own purposes. It'd be nice to say, kind of like express this in terms of y, let's say, that would be fine. Add 16x squared to both sides and divide by 24, something like that. What do you get? You get y has to be greater than, what is 16 divided by 24? Is that 2/3? Y has to be greater than 2/3 x squared. So y has to be positive. So what is it? It's the range where y is positive and also greater than 2/3 x squared. You know, you can realize if y is greater than something squared, that means it has to be positive. So you can actually just ignore this, right? You get that step of logic? I don't want to go too fast. I'm saying whenever this is true, then you already know that that's greater than or equal to 0. So this inequality here implies this other inequality, so you can just ignore this other one. And right there is your answer. Let's see if I'm right by looking at.
Would it be greater than or equal to 0 or just greater than 0?
So the question is what happens when it's exactly equal to 0, and the answer is it's complicated.
Okay.
It could technically be convex in some way, or it might not be. And
Okay.
For this class, let's just say everything has to be strict. The inequalities have to be strict. And I don't want to like teach you something which is technically wrong, but it actually isn't technically wrong if you say it as an if statement rather than an if and only if. So the function is convex if y is greater than 2/3 x squared. That is a true statement. Now, is it if and only if? Okay, then maybe not, because there's these other possibilities. But when I'm asking a question like this, over what range is this function convex? Let's pretend I mean like convex in the sense of strictly convex, and we know that it's convex because this rule has been satisfied. Let's say that. And so just give me this answer. I mean, let's see what I actually wrote for the theoretical drawings. How can I get out of here? Yeah. So this is what we figured out in our description. By the way, this is the sort of mathematically fancy way to write this answer. It's a set. You would answer this question over what range? What's the range? It's the set of all ordered pairs x and y, which themselves are elements of the real numbers squared. This is the Cartesian product of the set of real numbers, or this is just, any pair of real numbers. That's what this means. This colon here means such that any pair of real numbers such that y is greater than 2/3 x squared. That's actually the officially proper way to answer this question. If I ask something like this, though, I'm really looking for this condition here. Y is greater than 2/3 x squared. That's the way to tell me that's when the function's convex. Okay? I think that's the end of this section. You guys have any questions about the Hessian and this relationship between the Hessian matrix and the concavity and convexity? You know what nobody asked? How come you didn't ask this? Why aren't you more curious? No. Nobody asked, what about FYY? Aren't you curious? Why is the rule FXX instead of FYY? What's so special about XX? Can anybody answer that? There's an answer to this question. I'll give you the first part of the answer. There's nothing special about FXX. Nothing special about it. Okay, then the next question you should ask is, well, then why don't you also have to check that FYY is positive? Why don't you have to check that FYY is positive? Can anybody answer that? It's a little tricky. And it uses Young's theorem. Again, it uses Young's theorem. Because I can just tell you, why should I waste time? I don't want you guys to have to like stress over something that it's just an observation. It's not particularly important. But the observation is that these two numbers are always the same. These two numbers are always the same. So when you're taking the determinant, you're always going to be subtracting something squared, minus something squared, which will always be negative, right? It always makes it more negative. You know this, that anything squared is positive. So if you're subtracting something squared, you're making it more negative. That's easy, right? Okay, so if f of x is positive, the only way for the determinant to be positive is if fyy is positive also. Think of the alternative. If fxx is positive, but fyy is negative, that means when you take the determinant, you're going to get these two things multiplied together will be negative, minus something squared, which will also be negative, it'll definitely be negative. That's why you don't have to check FYY as positive. It's impossible for the whole determinant to be positive if FYY weren't also positive. So that's something you can skip. Does that make sense? It's just a little logic.
Yeah, that makes sense.
Great. All right, let's clear these drawings. And how much time do I have? It's 1:15. Want to give you like a half hour or something?
I just have a quick curious question about the Hessian matrix.
Yeah.
I know it can go like further than just a 2x2 matrix, but would we need a third variable if it was 3x3, and then I guess fourth variable if it was 4x4? Like you can't just have it. You can't have it be fxy and have it be a 3x3, right? You have to include z.
If it's a 3x3 Hessian matrix, that means there are three input variables to the function.
Okay.
Sure.
Okay. And they're always going to be squared, obviously, or like it's always going to be a square matrix.
Correct. Hessian matrices are always square. They're always symmetric also.
Okay.
But yeah, they can always be square. But the determinant might be 0. That's possible too. And you should think of that as being sort of this inconclusive case when the determinant is equal to 0. Okay. Do I have time to give you guys a little bit about total derivative? So here, I'm not going to give you any homework about total derivative, but I did give you some like optional problems to look at. I'm just wondering if we're going to have time on Tuesday to go over it enough, or if what do you guys think? If can I start telling you about it now and finish on Tuesday, or no time? What I was going to say is I was going to define what total derivatives were, and it has to do with this function of functions. So I'm debating, because of time constraints, what I can give you today. I think what I'll do is I still want to teach it to you on Tuesday. It's going to be hard to give you enough feedback for the exam, which is in 1 week beyond this. So if I do ask you anything about total derivatives, it has to be very simplified. And we don't have a lot of time. Let me just give you a real quick preview today, and then we'll talk more on Tuesday about what they are. First of all, before we even talk about total derivatives, it makes sense to realize that you can have a function of a function, something like what I have written here: z equals f of x of t comma y of t, or just to simplify that, z of x and t and y and t. This is like saying z is a function of x and x is a function of t. Z is a function of y and y is a function of t. This is something that happens a lot in economics, especially when t is time. But you actually may have an even more complicated case like this: z, where z is a function of x, which is a function of t, and z is a function of y, which is a function of t. But also z is directly a function of t. So you have these channels where how is t affecting z? T is affecting z in multiple channels. It's directly affecting it because of this last variable, and it's indirectly affecting it from these first two variables, in the fact that t can change x, which would change z. T could change y, which could change z. So here, what I've written here is just an example of, here's an example of a function z that has actually now 3 arguments, x, y, and t, where I've just written them out. It's x times y plus t x squared over y plus 3t cubed. This is an appropriate relationship between z, x, y, and t. And, you know, just as a preview, I'm not going to teach you today. I guess there's not enough time. But as a preview, what I would like to talk about is what is the total derivative of z with respect to t in this case, right? If I actually want to consider how does z change as t changes, and you know the instantaneous rate of change z with respect to t, it would be wrong for me to only consider the direct effect of t on z. Like if I took the derivative of this with respect to t and I just said, okay, well, here's from this term I get x squared over y, you know, I ignore this term. From this term I get x squared over y, and from this term I get, what's the derivative of 3t cubed? It would be 9t squared. If I got that, that wouldn't be the complete answer because obviously there's this effect on x and y that you need to consider. And basically, if you know the chain rule, this is just the application of the chain rule to this multivariate function. So if you wanted to find the total derivative of z with respect to t, you would have to take it, you'd have to consider that when t changes, x changes. And what is that effect? It's, you might call it just dz dx times dx dt. So let me kind of write that out here. I'm going to annotate it. And then I'll be done. Last thing. So as a preview of what do I mean when I say the total derivative of z with respect, oh, I can't go that low. It won't let me go that low. Ooh. Okay, dz dt. Just think of it as the chain rule, this thing that we've already talked about. It's like, okay, wait a second. There's dz dx. Those should be curly, they should be curly z's. dz dx. This is saying, okay, how does z change with respect to x? We should multiply that by dx dt because of the chain rule. This says, well, if I change t, that's going to change x, and x is going to change z. So this right here is like the effect of t on z through the x channel. I actually need to add to that dz dy, right, times dy dt. What is this part here? This is saying, well, if I allow t to change, it could have some effect on y, that's dy dt. And that changing y could have some effect on z, that's dz dy. So I have to take this part, the x channel, I have to add it to this part, which is the y channel. And now there's actually a third part I have to add, which is the direct effect of t on z. So that thing there is called the total derivative. And I'll give you some examples of it on Tuesday. Okay. This is called the total. It's not the partial derivative, it's the total derivative. Total d for derivative. Okay, so we'll do this on Tuesday. I'm not asking you about total derivatives on the quiz that you're going to take today. So, you guys have any questions about that? You can always say, well, postpone the questions until Tuesday. That's when we'll talk about it a lot more. Do you have any questions about the quiz? Okay. We're going to do the quiz. I did end up making it a a Blackboard quiz where you won't have to take a picture and send it in. I tried to make all the answers something you could type into your computer, and some of them are numerical answers, so you'll have to give the correct numerical answer. But many are multiple choice as well. There's quiz 3. Item is hidden from students. What I want to do is, it's 1:23 now. I mean, I'll give you 30 minutes, and I'll be around here. Maybe not, all of those 30 minutes, but yeah, I'll be around. if you have any questions, you could ask me. Sorry, the due date will be today, but I'll make it quite a bit later. How about 3 p.m.? I don't know. 2:30 p.m. Is that good? 2:30 p.m. today. Just so it's like an in-class quiz. It's the equivalent of an in-class quiz. And after due date, you can see all the answers. It's really a due time. Test presentation all at once. Once started, test must be completed in one sitting. Yeah, I do want that, I guess. Not that it'll make a big difference. Okay, submit. It should be available now. If I did it right. Let me make available. Sorry, look, it should be available now. I'm going to stop